Hello and welcome back to the FPGA PS channel. In today's video, I'm going to talk about the UART protocol and implement it as a VHDL module in a Vivado project. The first point about the UART is that it's a simple two-wire serial communication between the two nodes. Of course, there must be a common ground between the two devices. Each device can transmit and receive the data in the both directions. So the implemented module in the Vivado design will have two external ports, TX as the output and the RX as the input. UART frames contain a start and a stop bits, data bits between them, and optional parity bits. When the channel is idle, is held high. Why we need to keep the channel high when we don't want to transmit the data? UART is the asynchronous transmission protocol, and the transmitter needs some way to signal that the data bits are coming. The TX change the channel status from the 1 to 0, and it's a start bit that is change the idle high state to a low state. After sending all data bits, the stop bit indicates the end of the user data. A stop bit returns the channel to high or idle state. In this training, we are going to transmit 8 data bits. So as you can see here, each UART frame will contain 10 bits. In the UART module, the TX part is the parallel to serial converter, and the RX section is the serial to parallel converter. What does it mean? It means that for transmitting the data, we put the data 1 byte by the 1 byte, 8 bits here on the TX data port, and they are sent bit by the bit on the TX line. So this is converting the parallel data to the serial data. And the RX is the serial to parallel converter. We receive bits by the bits of the data, but the RX data port will deliver them to the FPGA section 1 byte by the byte. We can say that the chain of the serial bits are parallelized and converted to the 1 byte of the data. If we have the rate of 115,000 here, how much is the rate for the TX data port? So as we mentioned it before, each frame of UART contains 10 bits. So it means that the TX data has a rate 10 times less than the bit transmission here. So as you can see here, the data rate on the TX data is 1520 bytes per second. When we want to transmit the data with the UART module, we put 1 byte of the data on the TX data port, and we apply enable or valid pulse to the TX valid port. And then the UART module will grab that 1 byte of the data and transmit it bit by the bit on the TX line. So you can imagine that we have another module here in our Vivado design, for example, and that module wants to transmit the data over the UART protocol. That module needs to provide the data and the valid pulses by the proper rate for the UART module. Now consider that the provided clock is equal to the 50 MHz. How much is the distance between the two valid pulses for the TX data? As you can see here, the distance between the two valid pulses is equal to the 4340 clocks. In the same manner, when a receiver section receives a byte of the data, it will put the byte of the data on the RX data port, and it will assert a valid line for the 1 clock. So you can say here again, the distance between the two valid pulses from the RX data, it's approximately again equal to the 4340 clocks, and we will see that in our practical implementation in the Vivado by the help of the ILA. In the past, the old computer and desktop PCs, they were used to come with the RS-232, and RS-232 port allows us to connect the other UART devices to our computer. But the RS-232 port is almost obsoleted, and laptops and these days PCs, they don't come with the RS-232 port, and they always have the USB port. So what's the solution? The solution is to use the USB to UART bridge. the USB to UART bridge translates the UART signals to the readable signals to the USB. For example, in the evaluation board AC701, we have one of the USB to UART bridge, and when I check the user manual of this evaluation port, I can see that the pin U19 and the T19 of the FPGA are connected to this USB to UART bridge. So in my design, the UART module that I have in the VHDL will communicate to the USB to UART bridge over the pins T19 and the U19, and then easily, by the help of the USB connector, by the help of the micro USB cable, I can connect my evaluation board to the laptop that I have, and then a serial terminal will be able to display the transmitted signal and receive its signals. And then a serial terminal in the laptop will be able to show the received signal, and it also helps us to send the data to the UART module that we have in the FPGA. So now let's go and start our Vivado design. For this training, I use the VHDL code provided in a GitHub repository to save my development time. The repository was created by Mr. Jacob, and full credit for the original code and the video goes to him. The code is well written and functions as intended. As shown here, it's released under the MIT license, which allows both personal and commercial uses. I would like to express my warmest thanks to the Mr. Jacob for sharing such a high quality and useful resources. You can find the link of this GitHub repository in the video description, and you can download the code and also review the provided license for this GitHub repository. Created a Vivado project for the Artix-7 AC701 evaluation board, and I added all the VHDL code that I need for this Vivado design. When you go into the Git repository in the RTL folder, you can find multiple VHDL code, and then you need to add all of them as the new resources to your Vivado project design. Then you can create the block design and open it. In block design, right click and then add module and select the UART. You can see there is the VHDL file that his name is UART. This UART VHDL code is the top wrapper for the other component and the submodules that we have in the design, like UART RAX, UART TAX, clock divider, and debouncer. That's the top wrapper, and it contains all the necessary VHDL codes. The first mode that I want to try is to try the UART in the loopback mode. We connect the data out, as you can see here, to the data in, and we connect the data out valid to the data in valid. In this case, whenever that the Rx receive the data and then it assert the data valid, it will directly, the valid signal will be sent to our TX section, and the send data will be the input data for our TX section. And in the loopback manner, the data that we send from the host PC to the UART will be sent back to our PC. We need to provide the 50 MHz clock for the UART block. To provide this clock, I'm going to use the clocking wizard. In clocking wizard configuration, we need to make the input clock as the differential clock. For the outputs, we make the 50 MHz clock, since our VHDL module runs with the 50 MHz clock. You can also remove the reset pin. It makes our job easier for the clocking wizard setup. So now we make the input port of the clocking wizard as the external. In the AC701, I have an external clock equal to the 200 MHz. So I will set up the value of the frequency here equal to the 200 MHz. I can easily connect the clock 50 MHz to the input clock of my UART module. As I mentioned before, the UART module also have TX and the RX as the external port. You can find those pins here by the name of the UART TXT and the UART RXT. So I'm going to make them as the external pins. And then after the synthesis, we can connect them to the right pin from the FPGA pinouts. And then after the synthesis, we can connect them to the correct pins of the FPGA. The reset pin in the UART module is the active high reset. But here the Vivado, I don't know why, it's by the mistake showing that as the active high. You can easily connect it to the constant 0 if you don't want to use the reset pin of the UART module. Otherwise, you need to provide a synchronized reset with the clock 50 MHz for this reset pin. So to do that, we can add a processor system reset, and we connect the slowest clock to the clock 50 MHz. We connect the lock to the DCM lock. We can connect peripheral reset, the active high reset, to the reset pin of our UART module. And then we need to make the external reset as the external. And don't forget to make your external reset as the active high, because the push button will work as the active high signal. In the evaluation board that I'm going to use, there is the push buttons and its name is CPU reset, that I'm going to use it as the external reset for my UART module. We are almost done with the Vivado design for the loopback mode, and I just want to be able to see the data out and data out valid of the UART VHDL module when I'm transmitting and receiving data from my host PC. I'm going to add the debug probe for these two pins. Okay, so I also added the ILA. We need to increase the size of the sampled data with the ILA, then we will be able to see the data communication by the UART. So I'm going to increase it to the 65 thousandths of the samples. Then I can see multiple received data by the RX module. Now I need to go and add the top wrapper for the block design, and I let the Vivado to automatically create and handle it. And don't forget to set a new wrapper as the top in your design. Now I can proceed and run the synthesis. After the synthesis is completed, we will come back, assign the right pins from the FPGA to the external pins that we have in our design. The synthesis is completed, so I can open the synthesized design. And then in the I/O ports window, I need to assign the proper FPGA pins to each external pin. I shoot the screenshots of the pins that I need to connect. The first one is the system board clock. As you can see, the AC701 has the external clock that is connected to the FPGA pins of the R3 and the P3, and its type is LVDS25. I'm going to connect the differential pin of the clocking wizard to the R3 and the P3. The next one is the CPU reset, or the CPU reset push button that I mentioned during the design, and it's connected to the U4 and its type is SSTL15. The last one is the UART to the USB bridge. As I mentioned before, we need to connect two FPGA pins to the USB-to-UART bridge. That's the U19 and that's the T19. So the T19 is our Rx port and the U19 is the Tx port. Okay, I'm done with the I/O planning also. I can save my pins as the new XTC for the design. Then I can continue to generate the bit stream. Alright, the bit stream is also successfully generated, and I'm going to program my evaluation board. Now we should be able to send and receive the data to our evaluation board by the help of the UART protocol. So I'm going to open the Tera Term, and as you can see, the COM7, the Silicon Lab, is connected to my UART USB bridge. And we need to apply the same setup for that serial port. We select the 115,000. Our data width is 8-bit. We don't have any parity bit, and we have one stub bit. Because the UART module is configured in the loopback mode, as you can see here, whatever that I send to the FPGA, I will receive it back. For example, I can send A, B, C, D, E, and you can see when I press a key, I will receive it back from my FPGA. I also want to be able to see the received data in the ILA, So I will add the data valid to the trigger lists, and I arm the trigger on the rising edge of the data valid. Now I'm going to send multiple data to the UART by copying and pasting some value to the UART window. For example, I'm going to copy A, B, C, D, 1, 2, 3, 4, 5, and then I will paste them here. You can see that I received the same value, and here the ILA is triggered. When we look at the received data and T-valid signal, we can see that we are receiving 61, 62, 63, 64. If we compare them with the ASCII value of the A, B, C, D, we will notice that those values are completely correct. So if you measure the distance between the two T-valid signal, for example here, we can see that the distance, the number of the clock between the two T-valid pulse, it's approximately equal to the 4,400 clocks that we calculated before. It confirmed that the UART module is working functional in the loopback mode. The next mode that I want to try and test it, I want to send and receive some user data with the help of this UART VHDL module. So I'm going to add another module, and that's ASCII output generator that is able to generate some data with the proper valid signal, and we can directly connect that to our UART module. As we can see here, the ASCII output generator has a two output, value and the data valid. I need to disconnect data in and data valid. And then I can directly connect the value to the data in and data valid to the data input valid. This block also runs with the clock 50 MHz. The data generator has two inputs. The first input is the trigger in. On the rising edge of the trigger input, it will start to generate value signal and send them to the UART module. The mode allows you to select between the two different modes. The mode 0, in the mode 0, you will send a constant message from your FPGA to the host machine. For example, hello world from the FPGA PS. And when you set the mode equal to the 1, it will send a sine signal from the FPGA in your host PC, and later on I will display it by the help of the Python script. So to control the ASCII2 output generator, I need to add a VIO in my design and connect two outputs of the VIO to the trigger in and the mode select. So I added the VIO with the two outputs, and I'm going to connect the first probe to the trigger in and the second one to the mode select. Later on, by the help of this VIO, we can send the data from the FPGA to the host machine over the UART protocol. Alright, I'm done with the second Vivado design, and I'm going to generate the bit stream. Okay, the second bit stream is also ready, and I can try the new design on the FPGA evaluation board. We need to open the VIO dashboard, and we add the two probes of the VIO. So the first probe, it's controlling the trigger signal, and if I change the status of the probe 1 from the 0 to 1 and send the rising edge, I should be able to see the constant string appear in UART console on the Tera Term. So I'm going to trigger the send data, and as you can see here, the data is transmitted from the FPGA to the host PC, FPGA PS hello world 1, 2, 3, 4. So each time that I send a trigger, that I send a rising edge to the data generator, it will transfer the constant string to the UART module, and the UART module will send it to my host PC. You can see that multiple times a constant string is repeated here. So in this test, we select the mode 0 in the VIO. What if I select the mode 1? The data generator will start to generate a sine data and send it over the UART window. And if I trigger the data generator, I can see that the Tera Term is receiving the meaningless value. Unfortunately, the Tera Term is not able to display the data that the FPGA is transmitting to my host PC. In order to be able to see this transmitted data from the FPGA to the host PC, I wrote a simple Python code that it can receive the data from the serial input and display them as the graph. You need to set up the proper COM and the baud rate in the Python code. Before you run the Python code, you need to close the Tera Term because it already occupied the COM 7. So I close the Tera Term and I'm going to run the Python code. So the Python code have a graphic user interface. You can write whatever that you need to send to your FPGA and easily send it, and it can also receive the string data and display it in the second window. It has two different modes. It can receive the string or it can receive the data. If it's receiving the data, it will display it here, and for the received data you can select the data type. Like what is your data type? Is that unsigned integer, or is integer 16-bit, or is the integer 32-bit? So let's first try by receiving some string from the FPGA. I'm going to change again to the mode 0. That's when the FPGA wants to send that constant string to the host PC, and I'm going to trigger the input signal. I can see that I'm receiving the constant string successfully from my FPGA. Let's repeat it again. Okay, very nice. I can see that I receive it for the second time, and now I'm going to switch to the data mode, and I need to switch to the integer 8-bit because the data generator module is generating 8-bit data, because the data generator module is generating the signed values as the 8-bit integers. And now if I change the mode to sending the data and trigger the data generator again, I can see a very nice graph here. You can also clear the display data here and try it again. Okay, we can see a very nice sine curve here, and it confirmed that the UART module is also successfully sending the data from the FPGA to the host PC. If you want to have a little bit fun, you can change it to the int8. Of course, it's not the right data type, and then trigger the data transmission. And then we can see that you are receiving all the values as positive value, and the sine wave is not displayed correctly. So I'm going to again change it to the int a16 and trigger it. And I see the sine value is the larger amplitude because the Python code converts the received data to the type that you specify here. So if you don't specify the correct data type, you will not see the right values here. For this test, the right type was int8. Clear the plot and then trigger the data transmission.